So we're in chapter 8 now, Dr. Friedman's Physics 1 class, where we're studying momentum conservation, and whatnot. What is momentum? So a little review quickly that we started off in chapter 1, the beginning of this course, doing kinematics, right? We had the position, velocity, and acceleration. Those are related by time derivatives. We quickly moved on to dynamics, Newton's laws, culminating in the second law, sum of the forces, F net, or system, is equal to ma, the acceleration there. And from that, I think a week or two ago, we derived from the second law, derived the work energy theorem, that the work net on a system, I'll say this implies that is equal to the change of kinetic energy of a system. So consider say a system is just one mass. We have some forces. This work is the path integral of applied to Newton's second law. So you have these forces acting on etc. acting on this system, and it moves off in some direction. F equals ma. Work energy theorem. We have this so that the work done by the forces really will change the kinetic energy of this mass. That's what the work energy theorem says. The point is that something is lost going from the second law to work energy theorem, and that's the direction, right? All of these forces will change the kinetic energy of the system, but it depends. What's lost is the direction in this. The velocity in this direction would be the same. Its kinetic energy would be the same, where the velocity of the same magnitude in this direction. That ambiguity is not in the second law. It is a vector equation. So with that motivation, we want to define the what we call the momentum of a single particle, mass m, is mv. What's the value of that? Value of that is that we can rewrite the second law as F or F net is equal to dp dt. This is in the case when the mass is a constant, and you can see the generalization to the case when the mass is not constant. So if the mass were not constant, we'll have a product rule here. The second term in the product rule will be ma, the old ma. The first term, okay, let me go ahead and just do it. Tv plus the first term accounts for the possibility that the mass can change as the system undergoes this motion, which does happen for a rocket, for example. It's losing mass through its thrust. So we won't look at that right away, but just use this definition of the momentum to do some other things in this chapter. If we consider a system of masses, I'll just say two. These masses may interact. Typically, if they're in a system, they will be some force between them. They'll bump into each other, whatnot. So this is a system then we would say that the closed or not, the sum of the forces on this system, on both masses, or F net for the system, will be equal to what? Will be equal to F external. That is the sum of the external forces on the system. The masses in the system, two or however many masses that there are, will generally interact, but they will be equal and opposite forces according to the third law. So the internal forces will cancel. The total force, the net force on the system, on the sum of its parts, will be equal to the external forces, the net external forces. With this definition of the momentum, then, if the net force, the external force on the system is zero, then the momentum, the total momentum, will be a constant, will be, one would say, conserved. So say this is so that, summarize this, if the external force on a system is equal to zero, then momentum is conserved. Practically, what does that mean? It means you have some process, like in the problems we're going to look at now. There is something going on, some initial state, some final state, that the for momentum initial is equal to the after the thing that happens, momentum vector final. And this would be our application of conservation of momentum for this chapter. Let's look at this problem. I think it's number 819 from the text. Number 819. Squids and octopuses propel themselves by expelling water. They do this by keeping water in a cavity, then suddenly contracting the cavity to force out the water through an opening. A 7.5 kilogram squid, including the water in the cavity, at rest suddenly sees a dangerous predator. This would be our before state, I suppose. If the squid has this much water in its cavity, at what speed must it expel this water suddenly to achieve this speed for itself and escape the predator? So the before state looks like this. The squid himself or herself and the mass, total mass, yes, velocity for the system is zero, total mass is that, and the after state looks like one of these will be the squid, the other will be the water, and they go off in opposite directions, M1, V1, V2, right. So let's because the friction is small, we ignore viscosity of the water and consider the system as isolated, so that the momentum initial before is equal to the momentum final. P initial. It's not moving. V is 0, so this is 0. P final from this picture, respecting the vector character of it, of momentum, that's M1 V1 plus M2 V2, or because the momentum is conserved, P initial is P final, V2. And let's say that the water is M2, so its velocity is V2. We want to solve this for V2, velocity of the water. V1 is the velocity that the squid wants to achieve. So what are these numbers? M1.4, V1 10, M2, that of the water 70. Right, sorry. Taking data from 820. Rather, it's M1 plus M2 is 7.5. Sorry about that. M2 is 1.65. V1 2.7. Yes. So now, what does that give us? M1 we solve from the average side, the total mass minus M2. So divided by M2 times V1, 2.7. And putting that all in a calculator, I've got 9.57 meters per second. For him to attain this speed of 2.7, he must squirt the water out at this speed 9.57. So that should do it. For part B, you calculate the kinetic energies, K initial, and both of them will have kinetic energies, and you just do the usual, and that will give you the two kinetic energies. Right?